Welcome to the first video in Unit 4 for our class, where we'll be starting to talk about what are called carbonyls. This unit will be one of the most critical for the entire term because it will lay the foundation for our understanding of most of the rest of the reactions that we encounter through the rest of the class. So to get started, we'll look at a simple looking structure here where I've got a carbon and an oxygen that are double bonded together, and then that carbon has two other substituents that we're going to keep generic. We'll call them R groups for now. This carbon-oxygen double bond is what we mean when we say the word carbonyl. So this really is characterized by one carbon-oxygen sigma bond and one carbon-oxygen pi bond. And this subunit shows up in a lot of different kinds of functional groups that you might have encountered before. So let's look at some carbonyl containing functional groups. So to do this, we'll start by thinking about the fact that there must be a carbonyl, and I get to choose what's flanking that carbon in particular. On the left-hand side, let's say that this could either be a carbon or a hydrogen. So I'm going to call that R for now, but I'm going to say that R is equal to carbon or H. That means that it cannot be an oxygen or a nitrogen or a fluorine or any other element. So if I make this other side, this right-hand side, a hydrogen, I'm talking about an aldehyde functional group. If I change this hydrogen to some kind of a carbon specifically, I'm talking about a ketone. But there's a lot of other kinds of functional groups as well that have maybe slightly more complex looking structures, and in particular they will have what are called heteroatoms, so not hydrogen or carbon, bonded to our carbonyl carbon. One example might be a carboxylic acid. So we saw those recently when we started thinking about alcohol oxidation. Here we can see we've got an oxygen bonded to the carbon of the carbonyl. We can make a slight adjustment to this carboxylic acid. And instead of having an OH group, we could still have this second oxygen attached to the carbonyl carbon. But now we could actually have that second oxygen attached to a carbon of its own, and this would be an ester functional group. Alternatively, we could drop this oxygen altogether and think about, like for instance, a nitrogen, where this nitrogen is attached to either carbon or hydrogen. These are called amides. Note the D here rather than N. An amine has no carbonyl. An amide, D, has the carbonyl. You might also hear these called amides or amides. All of those are okay pronunciations. I typically say amide. There's a couple of other functional groups we can call out here. So rather than nitrogen, we could also look at, for instance, a chlorine or a fluorine or a bromine. We're going to call this an acid chloride. So kind of like an alkyl chloride, but instead of this chlorine being attached to like an sp3 hybridized carbon, this chlorine is attached to a carbon of a carbonyl. And there are lots of other examples. For instance, we could have sulfur instead of the oxygen. That would be called a thioester. We'll see those a little bit later in the unit. So here are some of your carbonyl-containing functional groups. I want to break them out along the lines of oxidation levels, though. So this carbonyl in an aldehyde is important also because this carbon is at a relatively high oxidation level. We know that it's at the +2 level, two different bonds to that oxygen. Remember that R can only be a carbon or a hydrogen in all of these structures that we've drawn. And that same thing is going to be true for a ketone, right? So the carbon here is at the +2 level. But if I look at the structures down here, these four structures on there at the bottom of the board, something changes. So this carbon of the carboxylic acid and the carbonyl has 1, 2, 3 bonds to oxygen. So we would say this is at the C+3 state. So carboxylic acids and ketones might be different on the basis of not only structure, but also the oxidation level of the carbon. Esters look to be the same way, +3, amide carbon, +3, and then our acid chloride carbon of the carbonyl also +3. We can actually characterize these carbonyls by their oxidation levels. So what we could say is that any type of carbonyl that has this carbon at the +3 oxidation level, we could call these carboxylic acid derivatives. In that, what we'll find over the course of the semester is that we can make any of these compounds or functional groups in the box from carboxylic acid. So the term derivatives comes from the concept of deriving, right? We can make them from the carboxylic acid. Aldehydes and ketones are fundamentally different. In order to get from a carboxylic acid to, say, an aldehyde, we would actually have to reduce a carbon. That's not the case for these carboxylic acid derivatives. All I'm doing is exchanging an OH group or something like that for one of the other substituents you see attached to the carbonyl carbon. So I think this is like a helpful sorting mechanism to identify things as either carboxylic acid derivatives, carboxylic acid derivatives. There's my spelling mistake for the video. Aldehydes and ketones are distinct in some ways, but not others, as we will see. So I'll sometimes call like compounds that look like aldehydes or ketones like the ketone class or the aldehyde class, just to distinguish that they are not carboxylic acid derivatives. So it's going to be important for you to know the names of these functional groups and be able to correlate them with structure. If you haven't already memorized those things, please do them in this unit, because I want to be able to use the names like, hey, think about an amide, and for that structure to be clear to you in your mind, right? It's going to facilitate discussion, and it'll make your life a lot easier as you work with the textbook, as you watch other videos, and as you do homework assignments and exams. So definitely these 6 functional groups you should absolutely know. I would also strongly encourage you to know thioester, which is literally this compound would replace the oxygen with the sulfur. And I'd also encourage you to learn about what an anhydride is. Right? So that's actually in your textbook. You can look it up online. It's a carboxylic acid derivative for sure. We'll be working with those a little bit in Unit 5, but it's not a bad idea to get them under your belt now. So in the next section of the video, what I want to do is start analyzing the structures of these kinds of functional groups, but I actually want to start by analyzing just the structure of the carbonyl itself. And it turns out that that will actually help us understand what's happening in all 6 of these functional groups, because they all have a carbonyl. And if we understand what the CO double bond brings to the game in terms of reactivity and structure, we understand a lot about what all 6 of these functional groups do. And that'll be a lot easier than memorizing a bunch of permutations for each of these 6 functional groups. What we'll find is that it's usually sufficient only to analyze the carbon and the oxygen of a carbonyl to know in a very general way how carbonyl-containing functional groups will behave. So let's go ahead and do that. We'll start with some simple things. We'll evaluate the carbon for geometry. So the carbon is sp2 hybridized. And that tells us a couple of things. It tells us that the angles here, these bond angles, are about 120 degrees. And it also tells us that the carbon is trigonal planar. That's worth knowing, this trigonal planar thing, because we know if the carbon is to serve as a site of reactivity, so for instance, if it's like a place where an electrophile would approach, or a place where a nucleophile would approach, for instance, we don't have to worry about stereochemistry, because those 2 approaches from the bottom or the top, those are equal to each other. We saw this in SN1 chemistry, where the carbocation carbon is trigonal planar. When we lose stereochemical control, we get a racemic mixture because of that feature. So what we can say is that carbonyls are not going to give rise to stereochemistry in reactions. That's helpful for us to know. It's one less thing for us to worry about. The other thing that we can do is actually analyze the electron distribution in the CO unit. If we look at those 2 elements, we know oxygen is more electronegative than our carbon. So we can say that carbon is partially positive and our oxygen is partially negative. We can also put that on the structure just to be clear. So our carbon is delta plus, our oxygen is delta minus. Because of this CO pi bond, I can also think about resonance. Where, I'm just going to redraw my carbonyl here. The electrons that are in the CO pi bond, or that make up the CO pi bond, at some level we could think about them being localized on either the carbon or the oxygen. If you're the electrons, you're going to choose the oxygen. That's where this concept of polarization came from in the first place, and we just looked at these electron negativity arguments. And that looks to me like we'll end up with a structure that looks like this. So we have these two resonance structures. They're not going to contribute equally to the actual resonance hybrid of a carbonyl. So, like, in other words, these two structures do not each give 50% of the actual structure of a carbonyl. This compound here has a carbon that has an unfilled octet, and there's charges where I don't necessarily need them. So we would expect for this to be the minor resonance structure. It might contribute 1 or 2 or 3 or 4% to the overall average, whereas this compound will contribute the vast majority of the structural features to a true carbonyl. What that tells me is that I have substantial CO double bond character, or strong partial pi bond between the C and the O, but I also have a buildup of a little bit of positive charge on carbon and a little bit of negative charge on oxygen, which is similar to what I was finding strictly applying electronegativities. One of the things that matters for us, though, is that we can see something special happening at this carbon here. This looks like a carbocation. The scene is getting me. There we go, carbocation. Cool, not exactly a spelling mistake, but whatever. What do we know about carbocations? Well, when we learned about them in SN1 chemistry, we learned that these are electrophilic centers. And because we're mixing in some of this carbonyl carbon character to our resonance hybrid, or rather carbocation character, excuse me, we can infer that in the resonance hybrid, the carbon is going to be electrophilic, right? So our second idea here is that carbon is, or carbon of a carbonyl, is electrophilic. Awesome. So we've just established, using structural analysis, and because of what we already know about carbocations, that regardless of what the R groups are, the carbonyl carbon is an electrophilic center. Nucleophiles will be attracted to that carbon in particular. That's pretty useful. We could actually use similar arguments to assess the oxygen. So what I'd like for you to do, with everything we've seen about resonance and bond polarization, I want you to predict how an oxygen would behave. What kinds of roles and reactions might you expect it to take? Pause your video and make your prediction. Looking at the pictures that we have for bond polarization and resonance and carbonyls, we see buildup of negative charge on the oxygen in both cases. In terms of the resonance arguments, we see that we have what looks like an oxygen anion, which when we thought about SN2 chemistry, we thought about as a nucleophilic site. We also saw in Unit 2 that oxygen anions can be bases. So the third observation we can make about carbonyls is that the oxygen will be nucleophilic and basic. As an important aside, nucleophilicity and basicity always go together, at least to some extent. Because if we think about what a base does, it donates electrons into a new bond to a hydrogen atom. What does a nucleophile do? It donates new bonds into donates electrons into a new bond. Those sound like identical activities. The word basic just means we're specifying the element that's the target for those electrons that are being donated. So this oxygen we could expect, regardless of our R groups, to be nucleophilic and basic. What we'll find in the next video in this unit is that these R groups do matter. They don't change these roles, but they do change the extent to which a carbonyl will perform these roles. So just like we talked about the concept of acidity as essentially describing the strength of a compound's ability to perform a role, these R groups will actually make the carbonyl carbon more or less electrophilic, and they'll make the oxygen more or less basic / more or less nucleophilic.